Today we learned how to measure area or volume of an irregularly shaped object by slicing the object up into easy to measure pieces. So just a quick note, problems 5 and 8 from the Gamma project are particularly tricky. There is a hint at this link. It's also posted in Moodle. Okay, so recall that our definition of the area under a curve is a limit of Riemann sums. So I've got this curvy function f here, and here I'm trying to estimate the area underneath using 5 rectangles. It's not a great estimate, but when I use 10 rectangles, it gets better. When I use 50 rectangles, it gets really good. When I use 100 rectangles, you can barely tell that I'm using rectangles. It almost looks like I'm just shading the area under the curve. So as the number of slices in n increases, the area of the slices approaches the exact area under the curve. So I'm using x as my independent variable in all these pictures, and then I accidentally switched to t here, so these should all be x's. So each of these f of x's times delta x's, these are the area of a rectangle. This one in particular is the area of the first rectangle. So it's easiest to see this in the 5 rectangle picture. So this is delta x, and the height of this rectangle is the height of the function f of x1. This is x1 right here, height of the function at x1. So the area of this rectangle is base times height, f of x1 times delta x. And then I do that for each of my rectangles, f of x2 times delta x plus dot, 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 f of xn times delta x. So then I rewrite that using summation notation. So I've got the area of one slice, that's my f of xi delta x. And then the area of all the slices is when I sum them up, all n slices. Then I'm going to take the limit as n goes to infinity, and that gives me the exact area under the curve. This is the definition of an integral, the limit as n goes to infinity of a Riemann sum. So this is the integral from a to b of f of x dx. So that was sort of a little review, a little reminder that the integral is defined as the limit of a Riemann sum, because we're going to use that concept a lot today. All right, so if I wanted to find the area of this triangle, this is a triangle with height 3, base 6. Its area is 1/2 base times height. 1/2 times 6 times 3 is 9, right? I can answer this question in 5 seconds. However, if I want to be really rigorous about it, I'm going to use a much more complicated process for this easy problem, because this technique is going to be useful in problems where the shape we're trying to find the area of doesn't have a formula. So we're developing this other technique for irregular shapes. Triangle is a nice regular shape. We know the formula for how to find its area. Okay, so I want to find the area of this triangle, and I'm going to use this technique of slicing. So I'm going to slice the triangle up into rectangles. I'm going to add all those areas up, and I'm going to take a limit. We're essentially building the integral as a limit of a Riemann sum. Okay, so here's my triangle. I'm going to build a bunch of rectangles and add them all up, okay? So I'm just going to look at a single representative rectangle here, one slice, and I'm going to find its area. Okay, so the area of this slice, this is a rectangle, so my slice is got some thickness, delta x, and the height of the rectangle is the height of the function at x sub I. So I picked a random x sub I to draw a slice. So this is a single slice. The area of that single slice is the base times the height, and the base is delta x, and the height is the height of the function at x sub I, so f of x sub I. And I should have called this f of x instead of y. F of x is negative 1/2 x plus 3. Okay, so the area of a single slice is f of x sub I delta x. So now I'm going to say, well, the area of all the slices, if I add them all up, I'm just going to add up all these slices. Each one has area f of x sub I delta x. And I'm going to do n rectangles. I'm going to start with x1 and go to n. So I'm going to build a bunch of rectangles along here where this is going to be x1 rectangle, and then I'm going to have another one here at x2, and then this is xi, and I'm going to keep going as I head over. This might be x, I don't know, 1000, and I'm going to keep going x 1007, right? So I'm going to have all these rectangles, n of them. I'm going to add them all up. I is going to go from 1 to n. And then the exact area will be what happens when I take the limit as the number of rectangles goes to infinity. So I take the limit as n goes to infinity of the sum, I goes from 1 to n, of f of x sub I delta x. Now this limit is a limit of a Riemann sum. That's the definition of an integral. So this becomes the integral of f of x. You drop the xi's when we change it to an integral, f of x. Delta x becomes dx. And then I need to figure out the bounds of integration. Okay, so I'm drawing these rectangles. This was my first one, right? So I'm starting at 0, and I'm doing a bunch of rectangles, infinitely many rectangles, between 0 and 6. So my bounds of integration are going to be 0 to 6 of f of x dx. Now I'm not quite done because I have a formula for f of x. This is the integral from 0 to 6 of negative 1/2 x plus 3 dx. Just check that formula. Yeah. And then that's a straightforward, use the fundamental theorem of calculus to evaluate that. We won't do it in this demo. We just need to get to the integral. Although maybe it'll be interesting just to evaluate this to make sure we get 9, right? We know the area of that rectangle is supposed to be 9, so let's just double check. So my antiderivative of negative 1/2 x plus 3 is negative 1/4 x squared plus 3x. Evaluate that from 0 to 6. When you plug in 6, you get 9. And when you plug in 0, you get 0. So this is, in fact, 9, as we predicted using the easy area of a triangle formula. Okay, so this next problem is concerned with finding the volume of a solid with known cross-section, meaning we know what the cross-sections look like. These are typically hard problems, but once you get a feel for what they're asking, it's not so bad. All right, we want to find the volume of the solid whose base is the region inside the circle x squared plus y squared equals 4. So let's just sketch that. X squared plus y squared equals 4 looks like this. It's a circle centered at the origin with radius 2. Okay. The cross sections are perpendicular to the x-axis and they're squares. Okay, so I'm going to draw some lines in the circle perpendicular to the x-axis. And I'm going to build a solid where I'm going to build a square on top of this green chord of the circle. So imagine coming out of the board or coming out of your screen, if you're watching the video of this, a square on top of this green line I've drawn, this green line segment. There's a square coming out of it. All the sides have the same length as this green line segment. So I've got some pictures of what this thing looks like. So I've got the x-axis, this is x, this is the y-axis. So perpendicular to the x-axis, I have some squares. So here's one, here's another, this pink one. But this is hard to look at in 2D. So I have a nice animation to help us get a good look at this thing. So this is the base. This is my circle centered at the origin of radius 2. X squared plus y squared equals 4. I'm going to show some chords of this circle. I'm just going to slice this circle up perpendicular to the x-axis. So I got a bunch of chords in here. So the solid I'm going to build is on top of each of these chords, imagine a square popping out of the screen. And this is going to build a three-dimensional solid. It's hard to visualize, so I'm going to drop the y-axis flat so that we can see this in 3 dimensions. Okay. Now I'm going to build just 4 example squares on here. So just squares coming out of the top of that circle. Rotate so you can see that those squares are on top of that base circle. Sweep one square through so you can see what this looks like. So I have one square sort of sweeping through the base. These are all my many, many cross sections of the solid. I'm going to create the solid. So now I'm sweeping the square through, but I'm not erasing it after it leaves the previous location. So you can see I've chosen a random x value. This x is being swept along the x-axis. And at each value of x, between -2 and 2, I'm building a square. Building a square on top of the base circle. Okay, so this is the final solid. Let's rotate it so you can kind of see what this looks like. And then there's our 4 representative squares. Okay, so we've kind of wrapped our brain around what this looks like. See if we can find its volume by slicing. Okay, so along the x-axis, I choose a random x value to build a square. So in red here, this is the x-axis. Draw it in red again. This is the x-axis, and I'm building squares at random x values along the x-axis. So here's one square. So it's hard to picture in the 2D, so I'm going to go in the 3D, so I'm going to go back to my 2D picture where I have this chord, right? And I'm going to build a square on top of this pink line segment. So I need to know the length of this pink line segment. That line segment is at a random x value. I randomly chose an x value where I was going to draw this thing. So this is x sub I, and I need to know that length. So one thing I could do is I could say, well, this is a circle of radius 2. So I'm going to draw in a radius, the center to the top of my chord, and I know that that's a 2. And I know that this distance is x sub I, so I could use the Pythagorean theorem to get my at least half the length of that chord. Okay, so see, I'll draw this picture one more time a little bit bigger. So this is 2. I picked a random x value to draw a chord, and I'm going to build a square on top of this chord. So I need to know how long it is so that I can calculate its volume. Okay, so if I want, this is x. That's the x value, the random x sub I picked to draw the location of my chord. So that's x sub I. My radius is 2. And this would be half of my chord. Let's call this like, we'll call that y. So to find the length of y, I know that xi squared plus y squared equals 2 squared. Oh, that's the equation of the circle. Of course, that's how x and y are related. That's the given equation of the circle. So if I solve for y, I get the square root of 4 minus xi squared. Okay, so I know that length. So I'm going to draw a picture of the square that pops out of the screen here when I build a square on top of that chord. So that chord has some small amount of thickness, right? Some small amount of thickness, delta x. So I'm going to translate this into a square slab. It's got some small amount of thickness, delta x, right? And then the length, the base and the height are determined by the length of this chord. Okay. So the length of that chord is double the square root of 4 minus xi squared. Okay, so the volume of this slice would be base length times width times height. My length is 2 radical 4 minus xi squared. My width is also 2 radical 4 minus xi squared. And my height or thickness is delta x. All right, so I'm just going to simplify this a little bit. So this is all multiplication. 2 times a radical times 2 times a radical. So I can do the multiplication in any order I want. 2 times 2 is 4. The radical times the radical cancels, and I have 4 minus xi squared delta x. I can distribute that 4 maybe, so I get 16 minus 4 xi squared all times delta x. So that is the volume of one single slice that's making up this solid. So on top of this circle, I've drawn one single square popping out of the board whose length is twice the square root of 4 minus xi squared. That's also its height because it's a square. And then its thickness is delta x. So what I'm going to do is I'm going to actually have many, many, many of these squares, starting over here at -2 and ending up here at 2. I'm going to have n of them, a whole bunch of them, stack them up. So the area of all, or the volume of all my slices I would say, well, the volume of one slice is 16 minus 4 xi squared delta x, and then I'm going to add up n of them. And then the exact volume of my solid is what happens when I take the limit of this sum. The limit as the number of squares goes to infinity. And that is the limit of a Riemann sum. That's an integral. Integral of 16 minus 4x squared. We drop the subscript of I when we translate to the integral. The delta x becomes a dx. And now I just have to think about the bounds of integration. And as I drew up here, I'm drawing these squares starting at -2, and I'm putting a square at infinitely many spots between -2 and 2. So my bounds of integration are -2 to 2. And then this is fairly straightforward to integrate in this case. I'll tell you it comes out to 42 2/3 is the exact volume of that solid. But in your activities, I ask you actually to not evaluate the integrals. I just want to make sure you can come up with the integral. And then evaluating them is a separate skill. Okay, so to summarize, we learned a really complicated technique to solve a very straightforward, easy problem. We sliced this triangle up into small rectangles, added all those rectangles up, and then took a limit as the number of rectangles go to infinity, and that creates an integral. And then the purpose was that allowed us to find the volume, that technique allowed us to find the volume of a really complicated solid that doesn't have a nice, easy formula for calculating its volume. So instead, I sliced this solid up where each slice was a square slab, right? Each slice was a square slab, and then you calculate the volume of a single slab, then you add up a bunch of those slabs, take the limit as the number of slabs goes to infinity, you create an integral. Okay, so summary of that process is on the next page. The basic procedure for using slicing to find area or volume is to draw a typical slice and label your diagram. Write the area or the volume of one slice. So calculate the area or the volume of that one single slice. Make sure it's a function of only one letter. Then you're going to write the sum of the areas or the volumes of n slices using sigma notation, followed by writing the exact area or volume by taking a limit as n goes to infinity, and then translate that limit of a Riemann sum to an integral. Calculate the value of the integral using antiderivatives if possible. Otherwise, you can use your calculator. In these group activities, you're going to set up the integral but not evaluate it, unless specifically told to do so.